All right. Hello, everybody. Great. So let's maybe start and just have me talk a little bit about what the main concepts are in this unit 7. Okay. Oops. So, all right. So unit 7 is about a couple of adjectives that we attach to functions, right? So, function f. Okay. Yeah. So again, as usual, if you have questions, feel free to like unmute yourself and speak. That's always great, right? So
I know we're just getting started, but I have a question prepared. Do you want me to wait?
oh yeah, no, go ahead. Then I'll decide whether to address it before or after the review. Go ahead.
Okay. I'm really confused about surjective, about like the definition of surjective functions.
Okay, okay. Can you say more about what is confusing about it?
Yeah, so I don't understand. So in the example,
Mm-hmm.
they had f of 1 equals b, f of 2 equals a, and f of 3 equals a,
Mm-hmm.
and that is surjective, whereas the one where all of the g's were equal to the same value, that was not surjective, and I don't understand what the differentiation there is.
Yeah. So okay. So let me start maybe by just some examples, right? So let me draw some possible functions from some possible sets. Okay. So let me call this function f1, and this is gonna work this. Let's change color, call this f2. Change color again, blue, f3. And do I have any more colors? F4, yellow. Okay. Let's talk about these 4 functions. And let's talk about first about F1. So is it injective and is it surjective?
Let's go with Ohio. This is Clement Vallandigham, a lawyer and politician from Ohio. He was going to court to defend a man. You know how they visited me?
So
Is their mic on?
I see NS. There's some background noise, so if you have the mic on and music in the background, either mute yourself or turn off the music, please. I see Sebastian. So we're talking about the red function, F1, and you're saying all items in Y must be mapped. In the second example, there's no item in X that goes to A in Y. Yes, yes. So I'm not sure I understand what you mean here, right? So let me, again, recall the definitions of being injected. Yeah.
Sorry about that. The first part of what I said there was in regards to the actual book. In regards to the first question you have on screen, I said that it is interjective and surjective.
It's injective and surjective. Okay, so why are you saying that it's injective?
It's injective because every element of X has a singular element in Y that it is mapped to.
Okay, let's be a little bit careful, right? Because I know that what you have in mind the right thing, but the way you're saying it's not quite right? Because if you look at the green example, it's still true that every element of X has just one element of Y that is mapped to, right? But the second example is not injective because you have 2 elements of X that map to the same element of Y, right? So what you really want to say is that if 2 elements in X are different, then the elements that are mapped to in Y are different, right? So let me write down real quick the definition of being injective. So if X1 is different from X2, then it has to be the case that f of X1 is different from f of X2. Okay, so this one is injective, right? Because, yeah, I mean, X has 3 elements, right? And the first element maps to this dot in Y, the second to this one, the third one to this one, and no 2 elements map to the same element. Okay, so what's the definition of surjective?
Definition of surjective is a function that every element of Y is the output via F for some input of element X.
Yeah, so if I want to squeeze it in the little room they have, I will have to say every Y is an f of X for some X. Every element of the set Y is the image of some element in X, right? So with this definition, I have here an element of Y that is not the image of any element in X. So in this case, F1 is not surjective. Okay, so F1 is injective, but it's not surjective. Okay, I see, let's move on to F2. And I see Ben saying that F2 is surjective. And I agree with that statement, right? Because how do you check that a function is surjective? Well, you say, okay, take this element of Y. Is it the image of some element of X? Yes, there's 2 elements of X that map to this element of Y. Let's go to the other element of Y here. Is there an X that maps to it? Yes. Is there any other element of Y? Is there any element of Y that is not mapped by anything? The answer is no. so it is surjective. And in this case, it's not injective because you have two elements of x that map to the same element of y. So if we call this x1 and this x2, x1 is different from x2, but f of x1 is equal to f of x2. Okay? So is everybody happy with the first two functions? Yep, great. Now the third function, as Ben is saying, is both injective and surjective, right? Injective is because no element of y is hit by more than one arrow, and surjective because every element of y is hit by one arrow, right? So this in particular is bijective. Or invertible. And finally, the last one is neither injective nor surjective. Right? It's not injective because of this guy right here that gets hit by two elements of x, and is not surjective because of this guy right here. Oops, that was not surjective. That is not hit by any arrow.
In number 2,
Yeah.
or in F2,
Mhm.
why is it surjective even though one of the y maps to two separate x's?
So y's do not map, right? Only x map, right? Y is map to, right? So being surjective means that for every y, there exists an x that maps to y, but I'm not saying that there must exist only one x that maps to y. There can be more than one, right?
Okay. Okay.
Right? In the definition of surjective, like it has to be the case that every y is f of x for some x. But if it's f of x for 27 different x's, that's fine, right? Okay, so far so good. Is everybody a little less confused about the definitions? Okay, so then I wanna ask you some questions. Let me wipe this clean. I wanna rephrase injective, surjective, and bijective. So I would like you to help me out and rewrite the notion of injective, surjective, and bijective in terms using inverse images. So let's start with bijective, which somehow is the most complicated one, right? So I would like to say that a function is bijective if for every y in y, and I want to say something about the inverse image of the set with one element y. So what should I say?
Something along the lines of there exists an X, I think.
There exists an x.
There exists an X, f of X maps to that Y.
Right, but so then how do you say it in terms of the inverse image of y, of this y?
Would it just be like f inverse maps, or is Y to X?
Say, try that again. So the inverse image of y, I think what you want to say is that it's a single element subset of x that we can call little x, right? In other words, like Nathan is saying, the cardinality of this set is 1, right? This is the same as saying there exists, so f inverse of y is equal to a single element set x, such that x is an element of x. Okay, so let me comment real quick. So Sarah wrote equals f of x. I don't know exactly what you're referring to, but we cannot say that f inverse of y is equal to f of x, right? This is not correct statement, right? And the reason is that this is a subset. Sorry, this thing here is a subset of x, right? Whereas this is and even if I put the thing here, this is a subset of y, right? So we can not have a subset of x be equal to a subset of y. Okay, it's really, really easy to get confused. So, but again, it's important to keep it straight. Okay, great. I'm glad it makes sense. Okay, so let's.
This is a notational thing, but why are the curvy brackets and parentheses around the Y where we're talking about the cardinality?
Yeah, so when you, good question. Let me address this question. So when you put curly brackets like this, and then you put stuff inside, right? Then this means that this is a set, right? Whose elements are listed inside the brackets, you know. In this space right here, right? So when I write f inverse of curly brackets y, right, I'm thinking not of y as an element of y, but I'm thinking of the subset of y that contains only one element, the element y, right? So it's just a distinction, right? So when you take a subset of y and you take the inverse image of a subset of y is a subset of x. And that's why I put the curly brackets around the little x, right? It's not, I don't just want to think of it as an element, but as a one element subset, right? Because we know that f inverse in general is not a function, right? So we cannot just say what is f inverse of an element. We can only say what is f inverse of a subset, and that is a subset. Okay, that help?
Yes, that did.
Okay, great.
Just out of curiosity, this is kind of a question from last week's homework, but this also kind of applies here. What is the proper way to like describe an inverse image? Like, would this be how you do it, or?
So, inverse images are sets, right? And there's a few ways that you can describe sets, right? If there's small sets, you can just list the elements, right? So if you want to talk about, you have set X, 1, 2, 3, right? And you want to talk about the subset that contains the element 1 and 2, right? One way to describe it is just circle it and say, this is U. Another way is to list the elements. Say U is the subset that contains 1 and 2. And another way is to describe the elements. This is especially useful when sets become very larger in infinite, right? So for example, you could say that this is very silly when X is just a set 1, 2, 3. But if I said X in X such that X is less than or equal to 2, right? This is a way to describe the set 1, 2, right? So here's 3 possible ways to describe the same subset of X, right? Either like pictorially, you just say, okay, here it is, or you list the elements, or you describe the elements by some algebraic property. It's all the X's in X that have the property of being less than or equal to 2.
Thank you, that's really helpful.
Great. Thanks for the questions. It's always very good to have questions to answer. Okay, so let's move on to surjective now. So again, I want to make a statement about surjective that starts with, for every y in y, and how do I continue? I want to say something about the inverse image of an element of y. Okay, so in red, I'm drawing a surjective function, and in blue, I'm going to be drawing a non-surjective function. And the reason it's non-surjective, right, is that I have this element right here that is not hit by any arrow, any blue arrow, right? And so the inverse image of this y is the empty set. And that's the bad thing. That's what you don't want to happen, right? So one way to define a function to be surjective is if for every element of y, its inverse image is not the empty set, which is equivalent, I see Nathan wrote on the chat, that's correct, is equivalent to saying that the cardinality of the inverse image is greater than 0. Okay, very good. Is this more or less clear for everybody? Okay. I'm gonna have to interpret silence as everybody's happy. So let's move on to,
On the,
yeah.
this is like a notation thing again.
Uh-huh.
Did you just leave out the parentheses on the inverse image, or is it just the squirrely brackets, or does it not
Oh,
matter?
sorry. I should this parenthesis, you mean?
Yes.
It should probably be there. Thank you.
Okay, that makes more sense. Thank you.
X. And again here. So the run parenthesis is just what you're taking the inverse image of, right? And then the curly parenthesis says, well, that's the subset. So it should be there. Thank you for the, yeah, good catch. Okay, so again, so let's say something about the inverse image of elements of Y, of single element subsets of Y that describes when a function is injective. Now, if we look at the red and blue picture here, right, the red picture gives me a function which is not injective. The blue picture gives me a function which is injective. Right? So what happens for the inverse images of elements of Y via the blue function? And what happens for the red function that causes the red function not to be injective?
Not every element of X maps to a Y. Or wait, no. That's wrong.
Yeah, so injective, when you draw this diagram with arrows, you really want to think of there's no two arrows that end up in the same place in Y, right? So the reason that this function, this red function, is not injective, the problem is right here. There's an element of Y right here that is hit by 3 elements of X. It's okay if elements of Y are not hit, and it's okay if they're hit by 1 element of X, but they cannot be hit by more than 1. So what can we say about the inverse image of an element of Y?
It goes to 1 element of X.
Not necessarily, right? Because look at this element here that's circled in blue, right? What is the inverse image of this element? It's the empty set, right? So the cardinality of this set is less than or equal to 1, right? You can have 1 element, you can have 0 elements in the inverse image, but you cannot have more than 1 element. And now notice that if we ask injective and surjective to hold together, right? This is asking the inverse image to be less than or equal to 1. This is asking for the cardinality of the inverse image to be greater than 0. Well, if you want a number which is less than or equal to 1 and greater than 0, then the only number that works is 1, right? So here's how these things are all equivalent. Okay, questions? Is everything okay? Thumbs up. Okay, all good, thank you. So then let's talk about surjective using images. Right? Remember that if you have a function from x to y, again, draw some function here. Here's a function, right? And then you have a subset u of x, right? Then the image f of u is a subset of y that consists of all the elements in y that are the image of some element of u. And then in particular, we said, okay, and the image of the function f, we're going to define it. So by definition, this is equal to f of the whole input set x. Right? So in this case, I take the whole input set x, and the image, in this case, is equal to f of u for this set u. Okay? So then the question for you is, how do I say f is surjective if, and complete the sentence with using the word, something that has to do with the image of the function. What does im represent here? So the definition of image of f, right, is right here, right, is f of the whole set x, right? So this is, if I want to write it down, is the set of all y in y such that y is equal to f of x. So in calculus, you call this the range sometimes of f. Yeah, sorry, this is im, not lm. Yeah. So the image of a function f, right, is always a subset of the output set y, right? Because the function f must send inputs in x to elements of y. But surjective, exactly. So surjective is if the image, if the image of f, try this again, is equal to all of y. So in particular, you see this example, f is not surjective because this element is not hit. This element of y does not belong to the image of f. Okay. Everybody happy? Any questions?
So this drawing is not surjective?
The function in this drawing is not surjective, right? Because there's an element right here, which is not the output for any input in X. And with this language, the image of the function is this red subset right here that does not contain this element, little y. That makes sense? Okay, I hope so. Okay, so let's see. I guess the kind of problems that you can play with, and I encourage each and every one of you to play with this kind of, to create problems, is suppose that you have functions that you can compose, f and g, right? And then see if it's, choose for each of these thing, like in an attribute. Say f injective, g not surjective, g composed with f bijective. And ask yourself, is it possible? Can I find an f which is injective, a g which is not surjective, and a g composed with f which is bijective? And if it's not possible, prove that it's not possible. So if yes, show an example. If no, prove it. Okay, so this, gives you, if you want, 6 to the 3rd possible exercises, right? Because you can just choose various options and then think about whether it's possible or not, right? So let me give you a couple minutes for you to think of whether it's possible to find a function f which is injective, a function g which is not surjective, such that the composition g composed with f is bijective. Okay, in the meantime, let me see is there a name for types of functions that map all elements of x to some elements of y, but not all elements of y. Okay, to answer Isana's question, those functions are simply called not surjective functions. There's not any other name. Yeah. Okay, does anybody have a guess for the answer to this question? You think it's possible? Okay. Can you come up with an example then, right? To show that it's possible, one has to show an example. Or
Wouldn't you, for an example, draw a like dot table like we've been doing where you label?
Yeah, you'd have to draw a dot table, or you have to give me like, you know, say that X is a set with two elements, call them 1 and 2. Y is a set with three elements, call them A, B, C. Z is a set with three elements, yada, 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 right? And then describe the functions, right? So there's an example means really constructing two functions and their composition like this. Okay. I see also not possible. Okay, in this case, be much nicer if we could all be in the same room so we could actually like have you come to the board and try, right? It is not possible. That is correct, right? Because, and let me prove it for you, right? So if I can draw. So we are saying that G is not surjective, right? So that means that there exists an element Z, right, that is not hit by any arrow in G. Like the arrows of G, they do whatever they want, but they do not hit this Z right here. So then in particular, regardless of what the arrows from X to Y are, no, the arrows of the composite first have to go from X to Y, and then they have to go from Y to Z following the arrows of G. And if no arrows from G hits Z, then certainly none of the arrows that you obtain by going from X all the way to Z will hit Z. Okay? So this seems a little bit clumsy. So how do we prove a little bit more formally? Well, let's use what we said earlier, right? So G not surjective is the same as saying that there exists an element of Z such that the F inverse of the subset given by the single element Z is the empty set. But then, well, G composed with F, sorry, not sorry. G is not surjective. So G inverse. G inverse of Z is not empty. But then G composed with F inverse of Z, which is F inverse of G inverse of Z, is then F inverse of the empty set. And the inverse image of the empty set cannot be anything by the empty set. Okay, so this is a formal proof that this is not possible. Right? And we have used the definition earlier of G being not surjective in terms of the inverse image. There must exist an element in Z such that its inverse image is the empty set. Therefore, the inverse image via G composed with F of that element is the empty set. And this implies that G composed with F is not surjective. And if it's not surjective, then it's certainly not bijective. Okay, great. So now I see a great question. So Berkeley's asking, what about if we switch? Oops, this is huge now. If we switch so that this is now not surjective, but this is injective. Is it possible that the composition is bijective? So let me clear up some room so we can.
Here the composition is a function going from x to z, correct?
Yeah. And so again, let's play with the. Oh, Jesus. So what we're saying here, right, is that this function is now not surjective, right? So there is some element of y which is not hit by arrows of x. But then the second function is supposed to be injective. So what happens? What's the problem here, right? Let's start from the element of y, which is not the image of an element of x. Let's look at its image right here. Let's call this little guy little z. And what is G composed with F? Inverse of the set that consists of little z. Empty. Yes. And because this is empty, this implies that G composed with F is not surjective, therefore not bijective. So this is still not possible. Okay, but now imagine again, so if you change this one more time, and we say, suppose that we ask F to be not surjective, and G to be not injective, and G composed with F, could it be bijective? And so, right. So here, my F is not surjective. My G is not injective. But G composed with F is bijective, right? Because if you follow, let me actually draw them green. The green arrows are the arrows of G composed with F, and you see every element of Z is hit exactly once. So in this case, this is possible. Okay, so we're basically out of time. Next time we will work on the group work. Next time, so I've decided I'm gonna assign the break rooms not beforehand, but I'm gonna let Zoom assign them automatically, because that way, last time what happened is that not every group had the same number of people. Some groups had 2 persons, had 5 or 6, simply because there are people not showing up. So we'll assign the break rooms right when the class starts. We'll work on group work. In the meantime, I really would recommend to make yourself a bunch of problems like this, right? Come up with, is it possible for, F to be surjective, G to be surjective, and G composed with F to be not surjective, right? Until you really get comfortable with what, how this concept actually work and how they operate. Yeah, okay, so I see that Nathan had a doubt, but it got resolved, so cool. If there's no last minute questions, stay safe and be well, and we'll see you all on Thursday. Yeah, thank you guys and girls. Okay, bye.